Okay, what I'm going to do is I'm going to try to motivate studying neutrinos, and to do that, to set some context. We'll spend some time on that at the beginning about the standard model of particle physics and what we understand about how the universe works at this level and where neutrinos fit in that picture. I'll talk a little bit about the early history and discovery, just because it's kind of fascinating. And then I'll introduce this idea of neutrino oscillations, which is what most of the neutrino experiments that are being done today really focus on. Certainly all the ones that I'll talk about, and then some of the things that we might discover through these kinds of experiments. Okay, so my conclusion slide first. So why neutrinos? So first of all, they're the most abundant known matter particle in the universe. So I'm comparing to like electrons, neutrons, protons. For every one of those, there's about 1 billion neutrinos in the universe, right? Outnumbers the other fundamental particles by a huge fraction. So that alone is a good reason to want to understand them. And in fact, they serve as excellent messengers from across the cosmos for regions that will become clear as we understand. You can use neutrinos to study things happening far distances away in the universe. We're going to ask the question if there are additional kinds of what we call sterile neutrinos, and I can explain what that means later, what I mean by that. And if so, what is... sorry about that. What is... I can't even say it out loud. It's awful. What is their mass? What role do they play in the early and current universe? And then we're going to ask a question about... So one of the amazing things about how we understand physics at the most fundamental scales, the most fundamental levels in terms of particles, is that there's matter and there's antimatter, and it behaves almost perfectly symmetric, right? And so one of the questions we ask ourselves in modern particle physics is, how is it that we live in a universe that's composed entirely of matter, right? Why in the universe that we inhabit today is it so asymmetric, given that all the fundamental rules that matter obeys is so symmetric? And yet here we are in this asymmetric universe of positively charged protons, negatively charged electrons. You know, where are all the anti-chairs and the anti-clocks, right? And that's sort of a embarrassing thing to not be able to understand from a particle physics point of view. We really understand what happened in like the tiniest fractions of a second after the Big Bang when the universe was started, except how it evolved so asymmetrically and isn't just a giant sea of photons, basically, which is what matter and antimatter would do when it annihilates. So that's a fundamental question that we have. We've looked a lot of places in physics for an answer. One of the places we haven't been able to look yet is with the neutrinos, and so that's what we want to do with some of the next round of experiments. And then, of course, do they have surprises for us? Because, as I'll show you, there's been a few along the way. Okay. So here is that standard model. Basically, all matter around us can be summed up in a short list of fundamental particles. Everything that you know and love is comprised of these three: the up and down quarks, which can assemble to make neutrons and protons, and the electron. And everything around you that you're familiar with is composed of those three particles. We've learned through experiments that there are all of these other sort of exotic, if you will, forms of matter. Now, they're arranged in this chart like this to highlight something in particular, and that is the relationship between these lowest level guys and their sort of siblings, if you will. So the up quarks that make up neutrons and protons, it turns out there are two additional kinds of quarks that are identical to it in every way except heavier. They're more massive. And matter always wants to sort of live in its lowest energy state. It's like matter in general is just lazy or something, right? And so higher mass objects will live if you can manage to create them, say in a particle accelerator experiment or something, they will live a very, very short period of time and immediately decay down the chain, right? Until you're left with the matter that's stable, thank goodness, that makes up everything around us. But nonetheless, this matter exists, and by understanding its details, we can learn a lot about the universe around us. Similarly, electrons have their heavy cousins, the muon and the tau particle, that share everything else about the electron. And then, of course, there are the forces. 4 fundamental forces. Gravity, which we will absolutely ignore, and you can understand why we ignore it by this column. Okay? So everything is normalized to the scale of what we call the strong nuclear force on this chart. I'll explain it in a minute. There are other ones which are not negligible. Here's one that's kind of 1/100th. That's the electromagnetic force. That's the one you're most familiar with. That's the one that makes your socks stick together when you pull them out of the dryer. And then there's the weak nuclear force, which is weak. It's 1,000,000 times weaker than these other guys. But then there's gravity that's just sort of off the scale at 10 to the minus 39. So when I'm dealing with a particle that has a minute mass, I care about the strong, weak, and electromagnetic forces, but I can safely ignore gravity. Okay? So we will do that. We're going to come back and talk about the weak force a lot, and that's kind of what makes neutrinos special, as I'll explain. Okay, so this, maybe I'll just skip over this. I've said a lot of this, but it's here in the slides if you want them. The key is maybe this third bullet, which is that the quarks can participate in all of those forces, the strong, the electromagnetic, and the weak nuclear force. They have the ability to experience all three of those forces. That makes them special. The three charged leptons, these guys here, they don't feel the strong force, which is what binds these guys together into nucleons, into neutrons and protons. They don't experience that, but they do feel the electromagnetic and the weak. And then there's the neutrinos, these neutral guys at the bottom, which are the ones we're going to talk about today, that match up against these charged guys, and they only feel the weak force, right? All three, two of the three, one of the three, ignoring gravity. And so that's going to turn out to be a key property of the neutrino. Okay, a couple things to point out. They were assumed to be completely massless when first discovered and inserted into this standard model. The standard model is just the term we use that describes this picture of fundamental building blocks and the four forces that they experience. Okay, so some things, some numbers about neutrinos. So I say down here that they outnumber other matter in the universe by a factor of 1 billion, and let me give you a sense of why that is. Where are some of the sources of those huge numbers? So first of all, neutrinos, because they interact weakly, and I'll explain exactly how weakly in a moment, but because they interact so weakly, once they're created, they kind of just whiz around and don't do anything, right? They don't get absorbed into materials. They're just there. That means that the neutrinos that were created in the very first instances of the Big Bang are still floating around in the universe today. They've been slowly cooling and losing energy, just like everything else in the universe as it expands, so they're very low energy, but they're there. And we can calculate how many we would expect, and we expect about 400 per cubic centimeter, or something like 10 million per cubic foot, right? And that's everywhere, right? That's in this cubic foot. That's in the cubic foot that I'm currently living in, maybe a few cubic feet, right? This number of neutrinos that are 13.7 billion years old in every cubic foot of space around the universe on average. All right? Many other things that were created in this moment, of course, have changed their form dramatically, have been assembled into stars or absorbed or whatever, but the neutrinos are still there. Okay, another example, supernova. So when a supernova explodes, when a star dies, right, and it cataclysmically explodes, which, by the way, is how how the heavy elements exist around the universe, right? All of the elements on the Earth, the carbon, the nitrogen, the iron, the everything, was born in a star and exploded when a star died as a supernova, and then collapsed through gravity into things like planets. Right? There's this famous quote by Neil deGrasse Tyson. Everybody knows Neil deGrasse Tyson, right? So what's his famous quote? It's not really a quote, but what's his famous answer to the question of, I think the question was, what's the most amazing fact you know? Right? This brilliant guy who knows everything about science and physics and cosmology, and some interviewer asked him, what's the most amazing thing you know? And his answer was that every atom in our bodies and in everything around us was born in a star and exploded out somewhere across the universe. And I agree with Neil, that's pretty cool. Okay, so when a supernova explodes, this is a supernova compared to an entire galaxy. So in the moment of its explosion, the energy is just absurd, right, when these things eject out. And 99% of that energy is in neutrinos that you're not seeing in this picture, because these are photons. So as bright as this is, it's 100 times stronger in neutrinos when one of these stars explodes. So there's another enormous number every time a supernova explodes. And in fact, a star throughout its entire life is just a giant neutrino factory. Because as we'll see, neutrinos are produced in nuclear interactions. nuclear decays, things like this. And so a star is just pumping out an incredible number of neutrinos. So again, let's ask how many. So this is me working on my neutrino tan. Now we'll see in a moment, actually, you can get a neutrino tan at night, but we'll come back to that in a minute. It was more dramatic or something with the sun shining on me, I guess. A really boring picture, there's no light. Okay, so we're 93 million miles away from the sun. So the neutrinos that were made in the sun about 8 minutes ago are hitting me now, right? Where's west? Yeah, it's over here. Okay, so let's ask how many neutrinos are passing through a 2 by 2 inch square in my hand. So I have this fancy PowerPoint graphic that's going to tell me. So this is counting off every 2 seconds. So every 2 seconds, another 3.4 trillion neutrinos from the sun that were born in the sun 8 minutes ago pass through the palm of my hand. Okay, so now we can do another calculation. If you imagine a sphere with a 93 million mile radius and a little 2-inch patch on that sphere, you can do a simple calculation of what is the fraction of this 4 square inches to the surface area of a 93 million mile radius sphere, right? And the sun doesn't just point its neutrinos at me. That would be rude, right? It does it isotropically. So you can turn that number that I just showed you into a total number by just the ratio of these areas, and this is it. Per second. That's how many neutrinos the sun is producing. And the sun is a really boring average star, right? So every star across the universe is doing this constantly and ejecting neutrinos. Neutrinos that don't then go off and interact with other things, that just fly around the universe forever. Okay? So big numbers and a lot of cool places where they come from. We've seen neutrinos from supernova. We've seen exactly 16 of them, I think. And that paper, not only, the paper that is those 16 events has been cited thousands of times. Okay. You don't actually have to look to the cosmos to find neutrinos. You can go to the grocery store and find neutrinos, right? Because neutrinos are produced in radioactive decay, including from potassium, right? Potassium-39 or whatever it is that's the radioactive isotope. All right. So, in fact, this is how neutrinos were realized to exist, was through radioactive decay. Famous story. They were measuring decays of neutrons, and they were measuring the energy of the electron that came out. And this is a two-body decay. Things just come out back to back. So you would expect the energy of the electron to just be monochromatic. It should just been the same energy over and over again because of this back-to-back nature of this interaction. But that's not what was observed. What was observed was a spectrum of energy from the electrons. And so it was hypothesized that there must be something invisible carrying away the other piece of energy. And that was the famous origin of the neutrino idea back in the 1930s. So it was actually Enrico Fermi who first calculated the mechanism for detecting a neutrino back in 1934, and his answer was basically it was not going to be easy. All right, so let's do a couple quick numbers. So in the 30s, they calculated. So it's this interaction. It's basically the opposite of this decay interaction. Instead, the neutrino is going to come in, hit the neutron, and create the electron and proton. Right? The reverse of that interaction can happen. It can happen for antineutrinos as well. You can calculate the cross-section for this, though, and it's bad. Okay? This is 5 times 10 to the minus 44 centimeters squared. It's a unit. It's kind of a funny unit, right? It's literally like area. It's saying, like, what's the probability for interaction? In your mechanics class, you might have calculated the cross-section for, like, hitting a sphere, and the answer ends up being the surface area, the cross-sectional area of the sphere, basically pi r squared. And so you apply that to subatomic particles, and you get kind of silly answers. But there's actually a unit which is 10 to the minus 27 centimeters squared, which is called a barn, which lore at least says that it comes from the phrase, like, hit the broadside of a barn, and they decided to use that term. But it at least gets you a reduced unit. But whatever, centimeter squared works. We're just going to compare numbers anyway. So for a neutrino that comes from the sun or from a nuclear reactor, this is what we expect. So now I'm going to calculate simply what I'll call the mean free path. So, given this cross-section and the density of lead, how much lead should my neutrino go through before it interacts on average? And so that's just putting some numbers into this formula and calculating this distance. So let's see what it gives us. So if we go to the sun, which are low-energy neutrinos actually, or we go to one of these power reactors, which is a very similar spectrum to the sun, what we call a few MeV energy, and you put these numbers in, you get an answer that's 10 to the 16 meters of solid lead that an average neutrino would pass through before it interacts. Right? If you convert that, that's a little over a light year of lead. A typical neutrino produced at a particle accelerator that I'm going to tell you about tonight is kind of in the 1 to 100 GeV, so 1,000 times more energetic. So you basically just get back that factor of 1,000. And now on average, we'll go through 10 to the 12 meters, which is a little better, but still about 1 billion miles of solid lead. So if you fill the distance between the Earth and the sun times 10 with lead, you might get your neutrino to interact. Okay? If you do this exact same calculation with a 1 GeV proton, the answer is this far. This is how far a 1 GeV proton, on average, will travel in a piece of lead, compared to whatever I just said, 1 billion miles of lead. Okay? So this is the experimental challenge. So Pauli, who first postulated, based on this spectrum measurement I said of the electron, it was his idea. And he wrote this famous letter to some conference that he wasn't able to attend. And there's this famous line at the bottom of the letter where he apologizes for not being able to attend because he had to attend a ball, which I think was a word for party in 1931. So anyway, but he writes this letter where he hypothesized this particle, and he describes its properties. And then later, has this famous quote where he says, he's hypothesized this particle, it can't be detected, and that's something that no theorist should ever do, except string theorists, apparently. Okay, so let's ask the question. Obviously, Wolfgang was wrong, or I wouldn't be in business, so let's find out how that was done. So basically, in order to overcome these numbers, you just have to overcome them with numbers, right? So you have a lot of small exponents, now you need some big exponents. So you need a source of neutrinos that's enormous, because yes, I gave you the distance for how long it'll take one neutrino to interact, but the other way to do it, of course, is just send a bunch of neutrinos and get one of them to interact. Okay? And then you need special, and by special, I also mean large. You just want to put a lot of material in the way of the neutrino's path and try to coax it into interacting. It's just a statistics game. All right, so this is one of my favorite things. This was one of the early ideas, the so-called poltergeist project. So right after the 1930s, there was the 1940s. And what did we do in the 1940s? We invented nuclear bombs. Nuclear bombs, because it's a big nuclear interaction, will produce an incredible number of neutrinos. So the idea, as I understand this diagram, the problem with a nuclear bomb is it tends to create vibrations, I guess, and rattle your detector. So the idea was to dig a shaft, a safe 40 meters away from your nuclear explosion. And you're going to evacuate this shaft, and then you're going to put, I love this, feathers and foam rubber at the bottom of the shaft. Okay? And then you're going to build this fancy detector, and at the moment you explode the bomb, you're going to release the catch, drop the detector. It's in free fall as the neutrinos pass through it, and you would see an interaction. You have to do this in order to have the thing floating when the bomb goes off, or else the detector will jostle around. So that was the idea. It was an awesome idea. I like this. Even if you're like, yeah, we saw one. Like, reproducibility in science is an important thing, and that's going to be an interesting one to try over and over again. But anyway, okay. So back to reality. So what did they actually do? They used nuclear power reactors. So these guys, Reines and Cowan, who went on to win a Nobel Prize for this work, they did this inverse beta decay reaction. So the antineutrino, which is actually what's made by a power reactor, comes out, hits a proton, which does the reverse of that decay, spits out a positron and a neutron. So this is the antimatter particle of the electron. Once it's made, an antimatter particle suddenly finds itself in a bath of matter, so it will immediately annihilate against some local electron and into energy, and that energy can be detected. And then the neutron similarly will eventually go and sort of capture onto an atom. And when that capture happens, it'll kick off a little bit of energy. And so you look for a coincidence of those two signals happening, and it's that coincidence that's so key to separate it out from accidental activity inside your detector. This happens over a few microseconds of time. So they did this, they witnessed it, and they saw the rate, the rate of their signal, of course, go up when the reactor was on and down when it was off, so they knew they were detecting neutrinos. So they sent a telegram to Wolfgang Pauli, saying they're happy to inform him that they've definitely detected neutrinos from fission fragments by observing inverse beta decay of protons. This is 1956. Remember the previous statement, Wolfgang's statement about how I should never hypothesize a particle can't be detected was 1931, right? So 25 years later, Pauli quips back, everything comes to him and knows how to wait. Okay. Quite a bit later, or a few years later, actually, not that long later, another 6 years or so, there was a second discovery, which was of the second type of neutrino. So up until this point, it was believed there was only a type of neutrino. It was all that was really needed to understand what was misunderstood at the time. A few years later, it was figured out that there is a distinction between a muon-type neutrino and an electron-type neutrino. So, surprisingly, a distinction was discovered through an experiment. And it's very simple to understand why. When the neutrino interacts, I told you it made an electron, or actually the antineutrino made a positron. Neutrinos always interact with their charged cousin, right? So a second source of neutrinos was made, and it kept making muons. And so that was the evidence that these were different. Okay. So then they decided, all right, let's give it a try. We're going to look at neutrinos from the sun, right? This thing that makes this enormous number of neutrinos. So they did that. This is the crazy, complicated chain and the flux that one expects. So this guy, Ray Davis, built this huge detector down deep in a mine to shield himself from other backgrounds. And this is cool. So Davis was actually a physical chemist, not a physicist. So what happens is the neutrino comes in, kind of does the same interaction. It's just on a neutron that's inside an atom. Okay? Basically does the same interaction, and it converts chlorine into argon. And this tank is a giant bath of cleaning fluid, chlorine. Same stuff you use to clean your bathroom. Right? And what he would do is they calculated that about every month or so, a few dozen of these interactions should occur and create argon atoms inside this giant Olympic swimming pool-sized tank of chlorine. And his job was to go in and extract the 30 or so argon atoms out of this many chlorine atoms and count them. 28 this month, or whatever. So he did that for 30 years. This is his data. This was the prediction in some weird unit, solar neutrino units or whatever, SNU. Okay? And this was his data. This is the average of that data over this 25-year time span. Well, about 100 sigma away from the theory. Right? About a third, actually. So what's going on? Either the theory is wrong, the experiment's wrong. They're both wrong, since these are both seemingly impossible tasks. Right? The theory had to calculate this to high precision. The experimentalist had to pull this out of this to high precision. Chances are they're both wrong. Or 2/3 of the solar neutrinos are no longer here at Earth even though they were produced in the sun. Those are the only conclusions one can draw. Okay, so they tried again. They looked for neutrinos from the atmosphere. This time they're going to look for both muon and electron-type neutrinos, because the atmosphere will make them both. The sun only makes electron-type neutrinos, but the atmosphere will do both. All that's happening here is cosmic rays are bombarding the top of the atmosphere and creating sprays of energy, and in that spray, neutrinos will get produced. The exact mechanism isn't so important for this. But the nature of that mechanism is such that it should produce about twice as many muon neutrinos as it does electrons. Okay? Just the nature of that propagation. So you go out and you make a measurement. So you build a giant detector. This is the Super Kamiokande detector in Japan. This is something like 50,000 phototubes or something. It's 50,000 tons of water. So they did this. So what this picture is, if you can't see, so this is as they're slowly filling this tank. This is two men in a boat, and they're cleaning the glass surfaces of the phototubes, going around, increasing the water another couple of feet, going around and cleaning the glass surface. If you haven't seen a phototube, they're these beautiful glass surfaces, and they're going around and cleaning them as they fill this thing. And so that's a 50,000-ton tank of water. I knew this one was going to be a little washed out. So there's a turquoise band, which is the prediction which on the electron side basically sits right on top of the data. And then over here, it's up here. This is the muon side, and this is the prediction. And there's this deficit in the data. Okay? Actually, it agrees for the neutrinos that are coming down on Japan. It disagrees for the neutrinos that are coming up from whatever's opposite of Japan. Okay? There's an asymmetry here that really is washed out by this plot, but the Monte Carlo, again, the prediction is here and then comes into agreement. So there's this asymmetry as you look. And what's going on here is it's different distances of propagation through the Earth. It turns out that's going to matter. This is going a very short distance down to the detector, which was underground, but like maybe a mile or so, versus going through the entire core of the Earth. Okay, so this is where we're going to need, in order to understand these two things, and this took 30 years, going back to Bocal's original measurements through Super K, and then that was, finally in 1998, I think, the discovery of neutrino oscillations hit the front page of the New York Times. Okay, so this took 30 years. All right, so the basic idea, so how many of you have taken quantum mechanics? Okay, so in quantum mechanics, we understand that you can think about particles in different ways, and you can think about different types of particles in states of superposition. Okay? So I told you that there are electron, muon, and tau. There's 3 different kinds of neutrinos. It turns out we now understand there are also 3 neutrinos of distinct mass. Mass 1, mass 2, mass 3. Good enough? Okay? And that the actual neutrinos you could either think of as nu e, nu mu, nu tau, or you can think of as M1, M2, M3. But really what they are is, quantum mechanical mixtures of those. No perspective is more right than the other. Right? So this leads to the following phenomena. And that is that if you hit 2 tuning forks that are just a few hertz different, right, what do you hear? You hear beat frequency. If you have 2 neutrino masses that represent a quantum mechanical frequency, and they are similar, they will beat. Okay? So for those of you who've forgotten this phenomena, there's a relationship between a particle mass and its frequency as a wave. If you have 2 of those that are only a slight bit different, you add them together and you get this beat frequency effect, right? Get this envelope. This equation explains how that happens. You see there's this sine term, which is going to give us this that we need. And it depends on a few things. It depends on what we call delta m squared, which is the difference of the square of the 2 mass states. So it's kind of like the difference of the frequencies of the particles. It depends on some mixing parameter, which is just an amplitude. And then it depends on the physical properties of how far the neutrino travels and what's its energy. Right? That's it. So a fundamental property of the universe, the masses of the neutrinos, how far you allow them to propagate and what energy they have, will determine literally a sine wave of oscillation of neutrinos. All right, so this is cool. So for those of you who have taken quantum mechanics, what textbook did you use? What is it? Shankar? Anybody use Griffiths? Okay. So in Griffiths, he makes you calculate this by working through the superposition of states. And there's a footnote, right? I use the 1995 version of Griffith's textbook. I don't know which version that was, 2nd edition, 3rd edition, or something. And when I was an undergraduate, we were assigned this homework problem, and we derived this. But there was this sort of unnecessary footnote in 1995 about this being, a simple, non-trivial quantum system. It is a crude model for neutrino oscillations. At present, this is highly speculative. There is no experimental evidence for neutrino oscillations. This was in 1995. Remember, 1998 is when the Super K result hit the front page of the New York Times. So things changed very quickly between 1995 and 1998 and have continued to evolve since then. But so from the time when I was an undergraduate to now, this entire field has sort of come into existence. And now there are just dozens of experiments around the world that do this. This is how they work. All right. So if you create a beam of one type of neutrinos, let's say muon type, As you propagate in distance, the composition of that beam, I'm purposefully saying I'm going to create a bunch of them. The composition of that beam will evolve. And it's a regular pattern. It will start as one type, it will convert into another, and then it will return to its original state, and it will continue to do that. It's an oscillation, it's not a transformation. Right? It's not like the neutrinos all change from one type to the other and that's it. It's an oscillation. So this is the ultimate neutrino experiment. You build a monoenergetic beam, and then you build a bunch of detectors. Right? And you would just map that out. You would see like a few more events here, even more here, then it would go back down. Right? That'd be sweet. That'd be really expensive. But it would be great. They won't let us build that. So instead, what we do is we build a neutrino beam that has a spectrum of E. So instead, I'm going to have, instead of having a fixed E with a variable L, I'm going to have a fixed L with a variable E. I'm going to have a spectrum of neutrinos, but I'm only going to put a detector at one place and sample that sine wave. Right? But what I expect is to see a distortion in my energy spectrum, rather than this beautiful distortion as a function of position. To create a neutrino beam is actually pretty straightforward. If you take an energetic beam of protons and smash it into something, it will make a spray of other short-lived exotic matter, in particular things we call pions. It's just a different configuration of quarks. And what do I say that anything that isn't, neutrons, protons, and electrons does as soon as you make it? It decays down into something more stable. When they decay, they make neutrinos. So basically, you can convert an intense, a high number of protons slamming into a target into a high number of neutrinos focused forward, right? And it turns out there's a great place to do that about 40 miles west of here, because there's a great neutrino or a great proton beam at Fermilab. So Fermilab currently creates 2 of these beams and is designing and planning to build a third one by using the protons to convert into these really intense neutrino beams. So what do you do? So an accelerator beam is kind of in the, let's call it 1 GeV energy range. So by moving the position of your detector, right, you can tune, like what you want in order to observe the oscillation is you want the argument of this sign to be of order unity, right? So that you see, so that this term doesn't just disappear. If this number is small, sine theta equals theta for small theta, right? You're gonna lose all of your oscillation effect. So you've got to tune your experimental parameters to dial in on a mass splitting that the universe has picked. So you can ask yourself, if I create a 1 GeV beam and I want to tune to this mass splitting, and don't worry for now how we discovered this, but we realized that the mass splitting was 2.5 times 10 to the minus 3 eV squared, some units, okay? You can see what you've got to do. I want to access this at 10 to the minus 3, which means I need, and if my E is 1 GeV, then I need my L to be something like 10 to the 3. So I've got to put in kilometers. Okay, that's the units for this equation. So I've got to put my detector something like 10 to the 3 kilometers away, which is exactly what was done. You build your neutrino beam at Fermilab, you put your detector as close to Canada as you can without going into Canada. All right? Turns out this is actually 750 kilometers for reasons that are historical. And you put a detector deep underground here. You fire your beam into the ground at about 3 degrees. And turns out 3 degrees is what you need if you want to leave the sphere 750 kilometers later with the radius of Earth. Okay? You do that quickly in this little plot. This is what you would expect to see at the far detector if neutrinos don't disappear, if they don't oscillate. This is just muon neutrinos, by the way, so they're going into the other kinds, let's say. This is the data. This huge reduction in what was seen as a function of energy. This is the ratio. You see that characteristic sort of sine function dip, right? And you observe this effect in the laboratory, where your laboratory crosses 4 states. Damn, 3 states. Okay? All right, so I'm almost done. So the next idea I want to just stick in your head, I said if you kind of dial the position given the accelerator beam. So the energy is important, but at an accelerator I can kind of only create a narrow window of energies. Where would I have to put my detector if I wanted to use an accelerator beam to measure this other oscillation? 100,000 kilometers away. Okay? All that means is an accelerator beam is a bad way to explore this mass splitting. You're going to want to use something else. And as a matter of fact, what you use is you use the nuclear power reactors because they create their neutrinos at 1,000 times less energy. And then you can put your detectors at a reasonable distance. So this has also been mapped out just as beautifully as this, but only using a different source for the neutrinos at lower energy. So you can put your detector, on our planet. Okay? However, what if I want to go the other direction? What if I want to explore larger mass splittings? What if I want to see there are neutrino states, right? If this is out of scale, obviously. If this is 10 to the minus 5, this is 10 to the minus 3, there's a whole range of splittings above that I might be able to access. And this is cool because I can bring my detector closer to access higher mass splittings with the same type of neutrino beam. And that's exactly what we're going to do. The thing is that the standard model only allows exactly 3 types of neutrinos, the 3 mass states and the 3 flavor states that we talked about before. So any discovery of communication with some additional state of neutrino is a major discovery, right? It would break that beautiful three columns of particles that we saw in both the quarks and the leptons in the standard model. And this is exactly what we're searching for. There are experiments to motivate this search that I don't have time to explain. It's not just a random search. So it turns out you can bring your detectors. This is Fermilab. For those of you who haven't visited, this is the famous building that looks like the symbol from the Atari video game. And so this is all on site. This is the source. These detectors are less than a kilometer from the source. And we're building multiple ones. We're cheating a little bit. We have a spectrum of energy, but we're also going to sample at multiple L. Okay? So there's 3 detectors. One of them is been built and installed. This is, there's a U Chicago grad student right there. I think he was the only one that was out there that day. This is the cryostat. I don't have time to explain how the detector works unless you want to ask me about it later because it's really cool. Oh, that was a bad pun. Sorry. But this is a giant cryostat. It's about the size of a city bus or something. Here's some more pictures of it. This is what's on the inside. This is called the time projection chamber. I got a cool story about that, too, if you want to hear it. This is sliding the time projection chamber into that giant cryostat before the end gets sealed up. This is just another picture inside of this time projection chamber. They decided the cheapest way to do this was to build it somewhere else and then come move it into position in the detector hall that was built for it. And the best way to do that was just to take the roof off and lower it down into the building so it would sit on the beam line. So that was done a few months ago. Okay, so finally, that's searching for so-called sterile neutrinos and for new types of neutrinos. One last thing. The thing I showed you earlier was a measurement of basically the disappearance of this kind of neutrino. This was the formula that explained it, and really explains it quite well. This is the formula that explains the transition, the subdominant transition, the other way. Okay? If I, instead of measuring the disappearance of this guy, if I actually positively measure the appearance of electron-type neutrinos in my detector, if I build a detector that can see electron neutrinos, and I measure, when these things oscillate, right, they disappear from one and come into another. And if I measure this positive signal appearance, this is the formula that describes it. Okay, we're not going to go through it, other than to say that the physics content of this subdominant oscillation is enormously rich. Because each of these terms is coming from different things. In particular, it's describing differences between neutrinos and antineutrinos. You can do this experiment with one and then the other and compare, and they should be different. They could be different. And it also has something about the ordering of those states that we drew earlier. Okay, so here, it turns out now we need to put the detector in a different location. This is in the Black Hills in South Dakota. It's not far from Mount Rushmore. There's another old mine there that we want to build the detector in. Turns out this longer distance really helps sample these terms in a way that this shorter distance cannot. We're also building special detectors that really have enhanced capability at that electron part of the signal. So a completely new type of technology, which is this time projection chamber I was just alluding to a moment ago. Give you a sense, I told you the one we built is about the size of a bus. So this is an old design, but it sort of gives you the right sense. And this little black speck here is to give you a sense of scale as a human. Okay? When you put your detector 1,000 kilometers away from your neutrino source, you need to make it really big in order to have enough events. That's why the short baseline program that we're doing at Fermilab is so important, because it allows you to build modest scale detectors, use them, demonstrate the technology before you build, detectors the size of a basketball stadium or whatever in the next phase. As I said, my conclusion slide was also my first slide. All right, I'm sure that was like way longer than I was supposed to go, but I'm done. Thanks.